Hello folks, we are going to talk about Introduction to Transmission Protocol. TCP, or the Transmission Control Protocol, is a protocol that operates at the transport layer of the OSI reference model, that is layer 4, and there are many TCP based attacks. So as security analysts, you will definitely want to be familiar with how TCP is intended to function. I will give you an example, and that example will be expanded upon later on in this course. When TCP establishes a session between two host devices, it goes through what is called a three-way handshake. The way that this works is the sender will send a TCP send message and the receiver will receive a receiver will acknowledge that by sending a SYNCAC. Now in this case, what is going to happen is, under normal circumstances, a final ACK would be sent back from the sender toward the receiver and we would have an established connection. But one common attack that capitalizes on the way that TCP is intended to function is that an attacker will send multiple send message. It will just flood with a whole bunch of send message and it will spoof the source address so that the receiving device, when it sends the SYNCAC, that SYNCAC goes nowhere and it goes to someone who doesn't exist, an unused address perhaps. If enough of these send message are sent, the receiver will use all of its resources sending SYNCAC message and it is never going to hear back from a sender. And so it consumes all of the resources and legitimate connection cannot be established. So again, this is just one example of how we can use the protocol against itself. It is a must to understand how TCP should function. Now TCP at layer 4 of the OSI model that we have talked about is also at the transport layer of TCP IP model. In terms of IP protocol number, it is protocol number 6. Now TCP provides a service to the upper layer. Now we remember there is an application. These applications want to send data and sometime they are going to send a reliable connection, and that is where TCP comes into play. TCP is what we call a connection-oriented protocol. Both devices have to set up a connection before the data can be sent. They are going to synchronize their session with one another, and then TCP will manage the flow. It will adapt to congestion, it will adjust to window size if need be, and overall it provides reliable transmission of the data. Now TCP establishes a pair of virtual circuits, and these virtual circuits are unidirectional. So we have one from the sender to the receiver and one from the receiver back to the sender. So it is said that TCP operates in full duplex mode. We can send and receive on each of those virtual circuits at the same time. Now as TCP sends traffic, it also includes a checksum, and that is how TCP verifies that the information that is contained inside the header has not been corrupted. Each of the TCP segment, as they are called, are numbered, and that sequence number is used to make sure that each segment is put in proper order, and we can use that data to determine whether or not we are missing something. So when I receive a number of TCP segment, the receiving device sends back an acknowledgement, and what that acknowledgement says is, okay, I have received everything you sent me, I am ready for the next segment. If a segment doesn't get acknowledged by a sender, then we are going to need a retransmission, or it is possible that session could be terminated. Perhaps the receiver device is no longer there. So TCP does some recovery service for us. It can request retransmission if we need to, and whenever we have segment that is sent, if that segment is not acknowledged, then the sending device know this is something I need to resend. So overall, that is the high level of how TCP function. Now let's look into the header where all of the data is contained, that helped me to do the sequence and the acknowledgement. Now this is a TCP header, and that TCP header is going to contain some information that is relevant to the upper layer. Now that information that is going to relevant for the upper layer is going to be the source port, this one, and the destination port here. In a sense, this controls how the application talk to the network, or how the application put traffic down onto the wire. So the 16-bit source port in general, as the session established, is going to be dynamic high number port. The 16-bit destination port is often going to be the port number that is assigned by IANA to a service. So for example, the HTTP protocol, which is used for web connectivity, use the well-known port number 80, and it is a TCP session. So TCP port 80 is web traffic. If this TCP header were being used to communicate with a web server, that 16-bit destination port would be port 80. For HTTP traffic, which is a variant of HTTP, it uses TLS to encrypt the data that is in transit. That 16-bit destination port number would be port 443. If we were using the file transfer protocol, then the port number would be 21. So there are a number of ports that are used. Another well-known port is Telnet. That would use TCP port 23. SSH will use 22, and there are just naming a few of the port that we might see here. SMT would be port 25, and so on. Now that's not the only information that is contained in this header that is going to be relevant for us. We have that 32-bit sequence number and that 32-bit acknowledgement number. Again, this is used to establish the session and to make sure that the traffic is kept in the right order. We have a 4-bit header length, a reserve field, and then we have a number of flags. Now these little flags bits get toggled back and forth during a session to indicate whether this is a sync message. So you can see the flag right there. That will be returned on if we are sending a synchronized TCP segment. We have the ACK that would be turned on. The bit would be set to 1 if we were acknowledging. So as we go through that three-way handshake, if it were a sync ACK, I would be synchronized in one direction and acknowledging the session as well. So I would have both of these bits turned on. We have an urgent bit, we have a fin bit, to let us know that we are finishing a connection. We have a reset bit to reset, a push bit, and so on. So there is number of bits that there are all used for session establishment and session management. We have that 16-bit TCP checksum again. We are going to make sure that the segment is not corrupted, that the header is not corrupted, and then we have a 16-bit window size. Now the way that this window size work is it a sliding window. If an end device start to receive too much data, and need you to hold off while it buffer up the data and process it. It can adjust that window size down so you don't send as many segments at once. Once it is recovered and it is emptied out, its buffer, that window size can be adjusted to a larger number, allowing you to send more segments. So these are the important fields here in the TCP header, and again they are used to establish a session. Many of the attackers that are TCP based attack are going to take advantage of the standard functionality of TCP. Changing sequence number, modifying destination port, changing the checksum, changing the bits that are toggled for your flags, and again messing with the window size. So next we are going to talk about